It's a pleasure to join you today. My name's John Chapman, a research professor at the Sorbonne University and Emeritus Director of the National Institute for Health and Medical Research in Paris, located at the Pitié-Salpétrière University Hospital. And I'd like to share with you today some thoughts on high-density lipoproteins. The reason being that we're going to focus down on HDL in the plenary session here in Maastricht on Wednesday morning. Now, the story of HDL really goes back almost a century. In fact, it goes back to Paris. And in fact, in 1929, Michel Machebeuf at the Institut Pasteur precipitated from horse plasma a protein phospholipid-rich fraction, if you will. And ultimately, that turned out to be high-density lipoprotein, and what became to be named high-density lipoprotein. Now, the interest in HDL was really triggered by a number of epidemiological studies in the States in the 1970s, which clearly indicated that in several cohorts, cross-sectionally studied or to a limited degree prospectively studied, indicated that subnormal levels of HDL cholesterol, in other words, below approximately 40 milligrams per deciliter in males and about 50 in females, that those individuals frequently exhibited an elevated cardiovascular risk, or a risk for premature cardiovascular events. And if you then trace the evolution of knowledge on HDL, there was knowledge of its structure, of the key apoprotein, A1, then knowledge of its lipid components, subsequently of mechanisms whereby HDL was produced in the liver and intestine, whereby it was remodeled in plasma by LCAT and CETP, indirectly by lipases acting on VLDL to produce surface fragments which sequester to HDL. And through studies of a series of mutations, the key role of a number of different proteins and processes was identified. Now, the early epidemiological work suggested that there might be a cardioprotective role that elevated levels of HDL might exert. That is to say, levels of HDL very approximately above 70 or 80 milligrams per deciliter, or approximately 2 millimolar. Those data were not particularly well founded, but nonetheless were suggestive. And to a large degree, regretfully, at the beginning of the 1990s, mid-1990s, a number of pharmaceutical companies decided that HDL was or could be a privileged target, raising HDL then to try to attenuate elevated risk in patients with an atherogenic dyslipidemia, and notably subnormal levels of HDL. Unfortunately, essentially all of those trials failed or were very partially positive, but all in all, the benefit-risk ratio was not sufficiently favourable for any of those pharmacological agents to see application or availability for patients. Now, there have been many questions as to why, but probably the simplest explanation, if you would excuse me, is that perhaps there was a little bit of a disconnect between our knowledge of the biology of HDL on the one hand and the idea that we could perhaps target some well-known mechanisms that regulate HDL levels, and if we could in some way accentuate their effects, we would ultimately find ourselves with elevated levels or raised levels in individuals at risk. Now, the reasons for that failure then, primarily lack of knowledge of the basic, but rather complex biology of HDL particles and of HDL function, and Another explanation is probably that we lacked the technologies, the molecular technologies, to really get down to the nitty-gritty, to relate the molecular components of HDL particles to their function. And so with the advent of omics, particularly proteomics, particularly lipidomics, to a lesser degree glycomics, and to a lesser degree RNA-omics, we're now in a position where we realize that there are at least 50 different proteins which can be detected in HDL particles, not necessarily in the same particles, and that there are well beyond 300 distinct molecular species of lipids. So this gives a scenario in which the lipidome, the proteome, come together to create a diverse array of HDL particles which display a spectrum of biological activities. So the big question for us now, and probably for the next decade, is how do we subfractionate, characterize individual particle species of HDL with specific functions? How do we relate those to different chronic diseases? For example, autoimmune diseases are known to be associated with highly defective HDL particles because of an inflammatory background. And we have the first notions whereby we can start to correct the inflammation, correct the proteome and lipidome of HDL, restore its normal functions. So I think the future is bright, but nonetheless, again, this will not be a simple story. HDL is an especially complex lipoprotein. It's not a single lipoprotein, it's many, and there may even be more than 100 different distinct species of HDL particles, each of them with a dynamic metabolism. So the future is exciting.